Guys, this is spanning tree lecture. So the task that we are going to cover in this video is why do we need spanning tree protocol, and then we will talk about what is this spanning tree protocol, what is the job of spanning tree protocol. So just let me first tell you, imagine there is no spanning tree protocol, nothing is there, you don't know even what is spanning tree, and what you are doing, you are just working in a switching topology. You have layer 2 switches, so I just did nothing but drag the switches here. I have switch 1 and switch 2. Now what you will do in your general scenario, you will just plug in one cable here and one cable here, and you have a very good connectivity in front of you, and you have some clients, some PCs here, and you have some PCs right here. But in this case, you do not have any redundant connection between switch 1 and switch 2. What I mean by redundant connection, the redundancy of the network depends if your main link fails. So the network have to be redundant if there is more than one link if something goes wrong, or you have to have some sort of backup. We don't have any redundancy, no backup in this case, because if this link fails, then there will be no communication between the PC1 and between the PC2. So that's why what the solution that came to your mind is, you say I just plugged in one port and I have a lot of ports. So instead of using only one link, I will go ahead and I will use two links of the links, so that you can have redundancy. Your data will be, you think that your data will go like this from this PC to another PC, and by chance if one link goes down, another can also still be there. But you don't know that if you are doing that, if you're using a redundant connection, a backup connection in your topology, then you are going to have a loop in your network. And what I mean by loop in your network, for that I have the paint ready. So I will just paste, I'll do one thing, I'll paste the whole topology here. Okay, names we don't know, we don't even need any names. PC, we just need simply two switch and the PC, that's it. We don't care at all about the names here. So let me take the snap and let me show you what I mean by there is a loop in the network. Okay, let's say you just go in here and assign the IP 1.1. Oh, too big. We have one. What do you mean by 1.1? See, generally if somebody says 1.1, it means that the last two octets are 1.1. It is like 192.168 1.1 or something like this. And in here we have 192.168 1.2. Now what you will do, you will simply go to one PC and you will try to do some communication. You will do ping 192.168 1.2, and immediately your PC will generate a ARP request, because it is a brand new PC or it is an old PC, and you just turn it on and there is no MAC address in the ARP table, because in order to do the communication in the ARP table you have to have the MAC address of 192.168 1.2. So we check the ARP table, PC's ARP table is empty, there is no MAC address. If you don't know what is ARP table, you can just think ARP table is a table in which you will be storing the IP address to MAC address mapping. And by default when you turn your PC on, ARP table will be empty, and you want to communicate with this guy. So in order to fill the ARP table, your PC will send a request that is known as ARP request, address resolution protocol request. That's only job is to ask this, what is the MAC of 192.168 1.2. And this ARP request, as you might have, I hope you have watched the previous videos, I told that all the ARP request is always a broadcast. And in this the source MAC is going to be of the PC1 MAC. Let's say the MAC address is something like this, ABCD and A123. I just took a random MAC address, and the destination MAC is going to be reserved for any broadcast, which is going to be, as I told you before in previous videos also, the broadcast MAC is 12 times F. So it is a ARP request. Now what will happen, the ARP request will go to the switch, and switch will do what? Switch knows that this is a ARP request, it is a broadcast actually. He knows that it is a broadcast. And one more thing to note here, that in this ARP request, which I'm not showing to you guys, is source IP and destination IP is also there. But the reason why I'm not showing you this thing here, because switches are blind to IP address. They cannot even read and understand IP address. Source IP is 192.168.1.1. Destination IP is 192.168.1.2. Of your next hop or your destination IP, destination network, for which you need the MAC address. So this is your whole packet, but when this whole packet will go to our switch will only look at this field. He don't know what is IP, the source IP, destination IP, or what is this thing. I just know that this is a broadcast and I'm going to flood it like crazy. So what do you mean by flood it? Flood it whenever, that is the default behavior of a switch. Whenever a switch receives, say, or any, not ARP request, but any broadcast packet with a destination MAC of 12 times F, it will only do one thing. It will send that broadcast out to every other port. So this MAC address, this ARP request, this, it will be flooded via this link also. Now see, the thing is, if you do this in reality, and it happens also on these two links, in on one of the link only the packet is going to be received first. For example, let's say it is being received first here, and then second time it is received here. So this is the red color thing is the first instance of that packet. It received here. Now immediately what this switch will do, it will do the same thing. It will say that I received a broadcast from this link, from link 1, and this is link 2. From link 1 I received, and it is a broadcast, so I will send it here and I will send it out this port, because whenever a switch receives a broadcast, it will send that packet out every port except on the which it is received. So this broadcast you received on this port, so you will not forward it on this port, but apart from that our switch have two other ports, so I will forward it there. Now what this switch will do, it will receive a broadcast on this port, so he will do the same thing. He will say I will send a broadcast, I will forward it, I will flood it to everyone, and again the broadcast came here, which was actually in reality originated from this switch only. It again received that same, and again it is going to do that same thing all over and again and again and again, and it will keep on happening. And more than that, we never talked about the broadcast that I received on this port for the first time. For that broadcast again same thing will happen, which will send out this port and send out this port also, and again it will receive the broadcast, and it will keep on happening again and again like this. And from here also it will be keep on going here again for every time, and also on this side. And this is for one ARP request, my friend. What if you are pinging a lot of IPs? You are opening your web browser. Whenever you access any website or everything, DNS request, ARP request, and a lot of thing goes. And a lot of those things are broadcast. If you remember correctly, DHCP, the first packet of DHCP is a discover packet. And even if you connect your cell phone or your laptop and you turn it on, your laptop will send a DHCP discover packet. That is the job of that packet, is to ask for IP address, and that packet is also a broadcast packet. So for that packet the same thing will happen over and over and over and over again. So this is also a very bad thing, and this thing is known as broadcast storm. So this broadcast storm is a very bad thing. So this answers our first question, why we need spanning tree protocol to stop this disaster. In one word, we don't want loop. It is a loop happening. So if you just leave the network like this, when the loop will stop? The loop will stop when one of the switch will crash. When they cannot handle the broadcasts processing anymore, the switch will crash, and then your broadcast will stop. Any other way to stop a broadcast? There is one way also. If you just go in there and if you just cut off the link. So if you cut off the link, what will happen? The broadcast storm will be immediately stopped. Okay, so if you do that thing, if the crash happens, then the broadcast will stop. So what is the other way to stop this broadcast storm? Is, as I told you, just go in there and remove one link. Because if you let me clean the topology, okay, looks much better now. Because if you go in there and if you remove the link, for example, if we have only one link in between, then what will happen? Let's make it invisible for some time, like this. We have only one link. So if you have only one link, then this broadcast will never go, and only on one link the broadcast will be received, and it will send that ARP request, that broadcast to here, and that's it. And even if a new broadcast will happen from this side, it will happen like this. It will go here, and it will go here, and it will go here, and that's it. So this is another way to stop it. Meaning what? Don't use redundant connections. Don't use the backup path. But what if you need redundancy in your network? This is not a perfect solution, because you have to have two paths. Okay, so what is the solution? That you should have redundancy maintained in your network, and there should be no loop. So the question is answered by this protocol. All these problems will be solved by spanning tree protocol. What spanning tree protocol will do? If you're running spanning tree protocol, then one of these four ports will automatically be in the block state. For example, let's think this port is going to be in the block state. What do you mean by block state? Block state is not the shutdown or down state. It is just, it will be on, the status will be up, the protocol will be up. If you do the command show IP interface brief, it will be up and running. But the block process, the block port, you cannot send any data and you cannot receive any data. So if you cannot send any data or if you cannot receive any data, then it will happen like this. It will be up and running. Broadcast will go on this link, broadcast will go on this link also. Then this broadcast received from the top link will be sent here, and this block port will not even receive this broadcast. It will not be processed by it because it is block port. On block port, always remember, data will neither be sent nor received. So you might think that isn't it just down? No, there is very big difference. Just okay, this is happening, you are doing communication and all the data is going like this. Always you are sending bytes or like KBs and MBs of data, and after some time something goes wrong and this top link goes down. So if this top link goes down, then you know what will happen. Immediately this block port will not be blocked anymore, and it will come into what is known as into forwarding state. So what do you mean by forwarding state? Forwarding state is a state in which you can send the data and receive the data. And if you from the beginning, if no port is blocked, let me tell you, this port will be forwarding, this will be forwarding also, this will be forwarding. I won't do that. Who will do that? Spanning tree protocol will do that. It will just select the specific ports and make it block. So it will just make this port block and the other, and if like see data, so this is blocked, meaning no packet, no data will be received on this. All communication will happen from top side only because both sides are forwarding. But after some time this link will go down. If this link will go down, immediately this switch will send a packet to this switch, and that packet is known as BPDU. And you might think that BPDU is a special packet. Actually, BPDUs are always sent between the switches, and when this will happen, it will send the BPDU, and it is their own communication, bridge protocol data unit, a packet which are used by the switches to communicate with each other. And when the BPDUs will be sent, this port will immediately know that it is a BPDU. It is not a data protocol, it is a BPDU, and something goes wrong. And if something goes wrong, then I will do what? I will not be blocked anymore, and I will move into forwarding. So if it is forwarding, then the data will, instead of this side, the data will be keep on going from here. So what spanning tree did for you, there is redundancy in your connection and there is no loop in your network. So let me just show you another example. Look here, we don't have this type of connectivity, you understand this. So what will happen if you don't run spanning tree? And the question you might be thinking, then this amazing protocol spanning tree, how can I start it? what is the way of starting the spanning tree protocol? So spanning tree protocol, you don't ever need to start. Spanning tree protocol is automatically running. Okay, you can just like go to your switch, and I can even show you. It's a working switch. Show spanning tree. These are all the data about the spanning tree. It means that your spanning tree is running. Okay, yes, if you want, I can turn off spanning tree, but if I turn it off, you know, the loop will happen. Let's go to switch 2, and let me show you there also. Show spanning tree. It is also here. Okay, so I want to show you one thing. I told you about forwarding and blocking, right? So one of these 4 ports are blocked. But first thing, we don't even know what is the naming convention or the number of port. So without that, you will never know. So click here and you will know that these are the numbers. In GNS, you might face this issue. Your interface number will overlap and you might be confused, okay, which port is which. So it is quite easy. Just take your cursor and put it on one link. It will tell you that I am connecting with E02 to E03. So this is E02 and this is E03. Simple as that. Now if you want to see which is forwarding and which is blocking, just click on the switch and the command you already know. What? Show spanning tree. It will show you that all the port state, we want to know about the state of the port, all of them are forwarding. Okay, I never told you that the port will be blocked on all the switch. Among these 4, according to the spanning tree, one port will be blocked. As you can see, E02 and E00. E02 and E00 both are into forwarding state right now. So let's go to switch 2 and see, do the same command, show spanning tree. E03 and E00. As you can see, E00 is right now forwarding. It is in forwarding. E03 is in blocking state right now. Okay, so this is just a coincidence. I also thought that this would be blocking. Okay, it might or might not happen like this. It don't depend on me, it depends on spanning tree. Spanning tree might even say that this port is blocked. But one of these 4 will be blocked, otherwise loop will happen. So as you can see, E03 is right now into blocking state. Okay, so let's see whether it is down or not. Show IP interface brief. As you can see, E03 is not down. Status is up and protocol is up. Status means whether it is administratively, like whether you have turned on with the command or not. So yes, it is on. By default, all the ports are on. Protocol means communication wise, it is on. But it can neither receive data nor send data because it is into blocking state of spanning tree. Otherwise, there will be loop in your network. So if you do something similar, and let me just do some things in between, let's change our topology and let's just put one another switch right here. So what I want to ask you, we have some offline students today as well, so tell me, if I turn all of them on, will there going to be any loop in this network or not? Because this question is quite important if you want to study spanning tree, because that was a very simple topology. Okay, now tell me, take your time. In this topology, same thing, I'll assign IP. Just imagine in your head, we'll make the communication. So if I make the communication and if spanning tree is not running, then the loop can happen or not? Tell me, yes, no. Yes. Yes, sir. Yes. Why? Because see, I'll explain it to you. Because the thing you will ask yourself, is there any redundancy in your network or not? Do you have any backup path? Yes, you have backup path. If you have backup path, there is always going to be a loop. For example, if you want to go from, okay, let me just open this in Paint again. If you want to go from this side, from PCA to PCB, let's make our mark a little stronger. Okay, you can go like this. If something goes wrong, this link also I have. So yes, I have two paths. That is known as having redundancy backup. So yes, there is going to be a loop, and if you are not sure, look at this example. A broadcast came. Switch will send the broadcast here. Switch will send the broadcast here. And again, this switch will do the same thing. I receive a broadcast, I will send it here, and he will do the same thing. I received a broadcast, I'll send it to other port. Other port by me, I mean it will also send it here also. And he received a broadcast, he will again send it here. He received a broadcast, again he will send it here. He will send it here. He received a broadcast, he will send it here, and it will keep on happening from this side, and also it will keep on happening from this side as well. So yes, there is a loop in your network. How you will stop it? It is already being stopped by the spanning tree protocol, because one of the ports here is going to be blocked. For example, it might be this port. So if you are curious that if this port is blocked, how my loop is gone, it is like this. I send the broadcast. See, you have to imagine, and if you are new, then take a pen and paper and try this and draw the whole thing. If you're smart enough, if you know, if you have done CCNA before or CCNP, then you will do this in your head. So the broadcast will go here, it will go here as well. But now what will happen, previously the switch was sending the broadcast here and here as well, but this is blocked now. On block we cannot send any data, so this broadcast will not be sent. And even more than that, when the broadcast was received here, in previous case it was sending it here, but now if it, even if it will send, it will not receive or process it. It will simply drop it. That's it. I don't know what you are sending, because I'm into the blocking state. And the very good thing about spanning tree is, oh, okay, it is blocking. But if in future something bad goes down or this link goes down, then this blocking, you don't even have to do any command, nothing, then this port will automatically become up. So what I'm going to do, I'm going to show you this whole scenario, and I will perform this on the GNS. I will show you which port is blocked, then we will go in there and we will just cut any link, and the other blocking one will automatically will come up. Okay, so just give me a second and we'll move on to the GNS. Okay, so let's move on to the GNS. And okay, we have the topology already, and I told you spanning tree is already running, so one of the port will be blocked already. So let's go to the switches one by one and check now. Let's go to the switch, show spanning tree. Is any port, can you see block?
No.
Okay, all of them are into forwarding. Let's go to switch number 2, show spanning tree. All of them are into forwarding. Okay, so don't get disappointed. See, it can never be wrong, because this is how the protocol works.
Yes, sir, block.
Yes, block port we have E01.
E01.
E01 is blocked. So this one, let me put something here. It is blocked.
Yeah.
No data can be, and the proof is right here. IU3 switch 3 E01 is blocked. As you can see, I have put it here. So now I'll just go here and I will simply see, you can go to the interface and shut down also. Some other problem can happen, or so it might be your wire or link might be damaged. So let's simply damage the link. But in order to, after damaging the link, I have to make sure that that port is also down here, E01. Okay, let's do this again. Let's do simply what the result. Let's leave that, because see, I trust GNS, but not 100%. 90% I trust them. On real, it will happen. Let's hope it happens here also. See, oh, very good, awesome. Listening, very good. I want to show you this thing also. Okay, I missed that. What I missed, when a port is into blocking, after that, as soon as it will get to know that something is wrong and I need to go into forwarding, then it will not go to forwarding like that. It will move from blocking to listening. It will start listening for any incoming frames, any MAC addresses, and then I will learn what switch always learn. Switch learn MAC address. So it will go to listening, then it will go to learning to learn the MAC, and after listening and learning, then it will go to forwarding. So as you can see, previously it was blocked. I link got like our main link, other link goes down, something bad happened there, and immediately after moving from listening learning, it will automatically move into forwarding. As you can see, oh no, it was in listening E01, and look, it is right now in forwarding state. Okay, so this was all about the basics of spanning tree. What is spanning tree, how it works, what it does, and why do you need it? And what kind of disaster will happen if there is no spanning tree? And if you want to know that what is the election, how the algorithm works, because it is in your syllabus of your CCNA and CCNP and even CCI. It is in Cisco. If you are learning networking, then you have to know, in order to better troubleshoot your network, that which port is going to be blocked. So for that there is a whole algorithm of spanning tree which I will post in the next lecture. So till now you have to know the basic of spanning tree, otherwise you can never understand the algorithm. And after, if you know the algorithm, even before I show you, you can tell me that this port is going to get blocked according to some values, like some priority, some MAC address, some bridge ID. You need to learn all about that. That is known as the algorithm of spanning tree. So let's do that into the next lecture. Okay. So if you like this video, just like and subscribe if you haven't done so before. Okay. See you guys.